Hello students. So in this video we will learn about the different combinations of the capacitor. So the first combination that we will learn here is series combination. So like as we have shown here in the diagram that there is a battery of voltage V and there are two capacitors C1 and C2 which are connected in series. Now as soon as we have connected them in series, then what will happen that the terminal where the potential is higher, it will immediately get a plus Q charge on its plate. So here we can see this C1 capacitor will get a plus Q charge on its left side plate, and because this is plus Q, then obviously on the opposite plate there will be a charge of minus Q. As we can see that the right plate of the capacitor C1 and the left plate of the capacitor C2, they both are connected with each other, and as we can see, but they are not connected with anything in the whole universe. How? As we can see that the dotted red line shows that this is completely isolated. So obviously when this capacitor C1 right hand side plate will get a charge minus Q, then obviously the left hand side plate of the C2 capacitor will get a charge plus Q, because initially also the net charge on these two combined plates was 0. So now also it should be 0, and the other plate will get a charge minus Q. So one thing we can learn from here is that whenever the capacitors are in a series combination, then and initially they are uncharged, then both the capacitors or all the capacitors which are in series with each other, they will all get the same charges. So next thing that we will see from here is that we have given denoted here points like A, B, C. So these points we have written here that because if we see the potential of A will be greater than potential of C by amount V. So we can write here VA minus VC is equals to V. Other places we have given some names like the potential difference between A and B. So this point A and B, they are across the capacitor C1. So across the capacitor C1, let us say the potential is V1, potential difference across the capacitor C1 is V1. As we can see here, we have written VA minus VB is equals to V1. Then VB minus VC, that means the potential difference across the capacitor C2, that we have given the name V2, and that can be written as VB minus VC is equals to V2. As we can see through a simple calculation that V1 plus V2, when we will add both of them, we will get VA minus VC, that is equals to V. So now let us write the Kirchhoff's loop law. So now when we will apply Kirchhoff's loop law, Kirchhoff's voltage loop, when we will apply here, then what we will get? Then we will get that once we started from point this, as we can start from point C, while we'll going, then we'll get the plus V potential rise, then we'll reach the charge, we'll reach the first capacitor. So we can write here the potential difference across this, it can be written as minus Q by C1. Why it can be written Q by C1? As we have studied earlier, that whenever we want to calculate the potential difference across a capacitor, then it is written as the charge on the positive plate divided by the capacitance, that is C1. While going further, we will get minus Q by C2, that becomes equals to 0. So we can clearly write from here, this will come out Q into 1 upon C1 plus 1 upon C2. So this is the one equation that we got from here. Now let us see the other equation, or we can write one more thing that we can learn, that V1 is the potential difference across the capacitor C1, that can be written as Q by C1, and V2 can be written as Q by C2. Fine. So now we want to calculate the equivalent of this. So for calculating the equivalent, we have drawn the another circuit. In this circuit, if you see that we have applied the same battery and we want the same charge to go through it. So when we will apply KVL in this, then we will get plus V minus Q upon C equivalent is equals to 0. So while calculating and while equating the equation 1 and 2, we'll get a very simple result, that is Q upon C equivalent can be equated to Q into 1 upon C1 plus 1 upon C2. It gives us a simple result, that is 1 by C equivalent is equals to 1 by C1 plus 1 by C2. So this is the formula for the C equivalent when the capacitors are arranged in series. So now let us go further for the calculation when the capacitors are arranged in parallel. So as we have shown here in the diagram, there are two capacitors C1 and C2. They both are arranged in parallel with each other. And we can see clearly that the potential difference between point A and B will be V. So both the capacitors will be across the same potential. So one thing we can write, that is Q1 by C1 will be equal to V, and similarly Q2 by C2 will also be equal to V. So here we can see that this will become Q1 by C1 is equals to Q2 by C2 is equals to V. While coming on to this side, when we have replaced it with the equivalent capacitor, then again we can say that these points again be called as A and B, and across this we can write this will become Q by C equivalent is equals to V. So if we see what is the relation between this Q and this Q1 and Q2, then we can say that the equivalent means we want the same amount of charge that must have gone through the battery. So in this case, if we see the amount of charge that has passed through the battery was Q1 plus Q2, so we want Q is equals to Q1 plus Q2. So while we're writing Q is equals to Q1 plus Q2, then we can write their values as Q from here can be written as C equivalent into V, and from here Q1 can be written as C1V and Q2 can be written as C2V. So by putting them and equating them, we can say that Q is equals to Q1 plus Q2, and on solving this by putting their different values, we will get C equivalent into V is equals to C1V plus C2V. We will get the value of C equivalent from here C1 plus C2. So this is the value of the C equivalent in the case of a parallel plate capacitor. Few things that we can remember from here is that if we see the case of the series, then in case of series, I had already told in series we have already learned this part, that if the capacitors are initially uncharged, then they both will have the same charge Q and Q, and we can see from here that the potential difference across them will be inversely proportional to their capacitance. Here we can see V1 is inversely proportional to C1 and V2 is inversely proportional to C2. And similarly, in the case of parallel plate capacitor, what we can say that they both will be having the same potential difference. So from here we can learn this thing, that the amount of charge that they will be getting will be directly proportional to their capacitance. Okay, thank you very much.